All right, let's begin. Inshallah, today we are going to cover the differentiation of implicit equations, right? The first category was general category, then we moved on to the differentiation of parametric equations, and now today, inshallah, we are going to cover the differentiation of implicit equations. So what is the difference? Basically, why do we call these equations implicit? Because usually when we used to look at the equations of the form y equals to fx, we used to see that y was the subject of the equation. Y was expressed in terms of x. And y was explicitly the subject of the equation. But an implicit equation is an equation which relates the variables involved implicitly. The variables are linked. There is an equation involving x and y both, but but one of the variables is not the subject. Usually we see that y is the subject and y is expressed in terms of x. But if y is not the subject, then this means y is implicitly shown. So the variables are involved implicitly. For example, the equation of the form xy plus y square equals to 2x. Now over here in this equation, y is not the subject of the equation, nor can it be made the subject. Even if we try to make y the subject, we cannot. Because over here is also y, over here is also y. We cannot make y the subject of the equation. In the equation, we cannot make y the subject, and we cannot express y in terms of x. So the equation xy plus y square equals 2x gives a relationship between x and y, even though it does not specify y explicitly in the form of y equals to fx. So there will be an equation, there will be a connection between two variables x and y, but the variables involved will be involved implicitly. How do we tackle such equations? The note says, to differentiate implicit equations, we differentiate each term with respect to x. So whenever we see an implicit equation, we differentiate each term with respect to x. And this is the first line that we write. Differentiate with respect to x. This is I'm going to write in the questions that I'm going to solve, right? But firstly, I'll deal with a very simple explicit equation that we used to deal with in AS level and even in A2. Why example number 1 tells us, but I'm going to give you a different perspective over here now. A different perspective, and you will see this equation being differentiated normally just like we used to do in AS, but a different perspective I need to give over here. So let's look at that different perspective that I'm trying to give you over here. So y was expressed in terms of x. Y equals to x cube minus 4x square, right? So y was equals to x cube minus 4x square, and this is an explicit equation. This is not an implicit equation. Why is this an explicit equation? Because y is the subject of the equation. Y is a function of x, right? Y is a function of x, and that is why this is an explicit equation. So whenever we used to differentiate such equations, we used to do this directly. We used to differentiate and we used to write that we are obtaining the gradient function dy by dx. These steps were not usually shown, but I have to get you through these steps now. I have to pass you through these steps so that you know what the mechanism was actually, but we were skipping these steps. Why? Because at that point in time, these steps were not relevant. That were not mandatory. Even now, they are not mandatory. We can directly give dy by dx if we have by the subject. But these steps are very important if we need to understand the entire process. So usually what we used to do in AS was we used to, as soon as we used to see y, we used to differentiate and we used to write dy by dx. And the other side, we used to differentiate, x cube becomes 3x squared, 4x squared becomes 8x. This was the normal procedure that we used to follow. But if I give you a different perspective to think, the question says differentiate with respect to x. Now, what is the meaning of differentiate with respect to x? Differentiate with respect to x means d by dx, d upon dx. And in maths, the rule is whatever we do on both the sides. If there is a square root and we have to remove it, we square both the sides. If there is a square, we have to remove the square, we take a square root on both the sides. Similarly, if we have to differentiate an equation, we will differentiate both sides with respect to x. So we are going to take d upon dx on both the sides. Whatever is being done on one side, we need to do that on the other side as well. So when we used to differentiate, even in AS level, when we used to differentiate, what we were actually doing was we were differentiating both sides with respect to x. So we were taking d upon dx on both the sides. So let's try this process over here. If we take d upon dx on both the sides, then d upon dx will be applied on y. Differentiate with respect to x, y, and differentiate with respect to x, x cube minus 4x square. Now, as we were trying to differentiate y with respect to x, it could not be differentiated. Because if we are going to differentiate something with respect to x, then there has to be x involved in it, then only it can be differentiated. But if we are trying to differentiate y with respect to x, then there's no element of x present inside that. So it will not be differentiated. And as it will not be differentiated, it will be attached to d upon dx. As there is nothing x, there's no kind of x involved in y. So when we are going to differentiate y with respect to x, y will not be differentiated. Rather, it will be attached with d upon dx. And that is why we used to see dy upon dx. This y used to get attached with d upon dx, and we used to see dy by dx as a result. But on the other side, when we used to differentiate with respect to x, then inside the bracket, the function involved was having x inside. There was x involved inside the bracket. So that was differentiated. And that is why when it was differentiated, we used to get 3x squared minus 8x. So that is why as this side was actually differentiated, this could be differentiated because it involved the variables x. That is why d upon dx was being applied on that. And the equation actually got differentiated. And that is why d upon dx vanished. But on the left side, as there was nothing inside y, there was no x involved. There was only y. And it could not be differentiated. So d upon dx, the operator, this d upon dx, the instruction of being differentiated, we are giving an instruction of differentiating, right? So d upon dx when applied on y could not be differentiated. So d upon dx remained and y got attached to it. So that is why from here we used to get dy by dx, and this particular thing was differentiated to give us 3x squared minus 8x. What I'm trying to communicate, people trying to get it, समझ आ रहा है मैं क्या कहना चाह रहा हूँ? मैं क्या कहना चाह रहा हूँ उसको मैं एक दफा अंदाजे बयां को उर्दू में भी बयान करता हूँ. Normally y in terms of x express हुआ करता था. यहाँ y in terms of x express नहीं होगा अगर, तो फिर वो implicit equation है. बट अभी मैं explicit equation में ये बता रहा हूँ कि जब हम differentiate करते थे तो हम दोनों साइड को differentiate करते थे with respect to x. बट लेफ्ट साइड पे क्योंकि y हुआ करता था जो कि with respect to x differentiate हो नहीं सकता, उसमें x वाली कोई चीज नहीं है, तो वो d अपॉन dx के साथ अटैच होकर dy by dx बन जाता था. जबकि राइट साइड पे क्योंकि x वाला फंक्शन मौजूद था तो वो डिफरेंशिएट होके हमें 3x स्क्वायर माइनस वो डिफरेंशिएट हो जाता था. और क्योंकि डिफरेंशिएट हो जाता था लिहाजा d अपॉन dx की इंस्ट्रक्शन वहां से हट जाती थी और डिफरेंशिएट होके जो फंक्शन आता था वो हम लिख देते थे. तो दिस इज द बॉटम लाइन. So the second example tells us that if we are differentiating y with respect to x, then it will not be differentiated, and that the d upon dx will remain, and the y will get attached to d by dx, and we'll get dy by dx. This has already been implemented in example number 1. I've separately written it as well, just to let you all know that this is the rule, that if we are differentiating something, if we are differentiating y with respect to x, then it could not be differentiated and it will be attached with d upon dx to give us dy by dx. Now, if you look at the third example, now d upon dx of y cube. Now, y is a function and there is a power on that function. So if we recall composite functions, even in general category, we recapped the concept of AS level composite function. Then that if there was a function and if there was a power on top of that, and if you are going to differentiate it, then first we'll multiply the power. Then the power gets subtracted by 1. And during this process, the function remained inside the bracket intact. The function remained intact. And then the differentiation of the function was multiplied, right? So this was the rule. Multiply the power, subtract the power by 1, and then the differentiation of the function inside the bracket will be multiplied. This was the rule that we used to follow. So even if there is y cube involved, although y cannot be differentiated with respect to x, but if we treat y as a function, then we can at least deal with the power, right? So let's deal with the power first and treat it like a composite function. Multiply the power, subtract the power by 1. I've written it like this: y whole cube. The first step, treat it like a composite function. And the function inside the bracket is 1. The first step, multiply the power and subtract the power by 1. And then multiply the differentiation of the function inside the bracket. So when we are going to differentiate y with respect to x, then it will not be differentiated and we are going to get dy by dx. So first we dealt with the power. When there's a power, we deal with the power first. And when we are differentiating, we deal with the power first. We multiply the power, we subtract the power by 1. During this time, the function remained intact. That is y remained y. But later on, when we were multiplying the differentiation of y with respect to x, it could not be differentiated and we got dy by dx. So whenever it is a term of y, it will not be differentiated with respect to x and we'll get dy by dx. In implicit equations, we always differentiate with respect to x. We always differentiate with respect to x, and if there is y involved, it will not be differentiated, and out of that, we are going to get dy by dx. जहां जहां y इन्वॉल्व होगा वहां अल्टीमेटली dy by dx जरूर आएगा, क्योंकि हम पूरे इक्वेशन को विद रिस्पेक्ट टू x डिफरेंशिएट कर रहे होंगे, और अगर y की इन्वॉल्वमेंट होगी तो अल्टीमेटली dy by dx वहां से जरूर ब जरूर हासिल होगा. Then if we look at the fourth example, 3y power 4, then again the same rule. First, deal with the power, differentiate the power. This means multiply the power. We are differentiating, we multiply the power and we subtract the power by 1. So 3y power 4. 4 gets multiplied, it gets 12. Y remains intact, the power becomes cube. Then when it is the time of y and we differentiate it with respect to x, it could not be differentiated, so we got dy by dx. Okay, then I've also written on the side, and if I'm differentiating with respect to x cube, then it could be differentiated. Even if we look at x cube like a composite function, then we multiply the power. Although we never looked at it like a composite function, the differentiation of x cube was simply 3x square. But even if we look x cube like y cube, then we can look at it like that way as well. उस तरह भी हम देख सकते हैं इसको. Let's suppose if it's x cube, then we multiply the power and we subtract the power by 1. And then if we multiply the differentiation of x with respect to x, then the differentiation of x with respect to x is 1. So there was no use of writing that, and that is why we got 3x squared. That is why we never thought that way, and we used to give the differentiation of x cubed directly as 3x squared. And if I'm writing as well that let's suppose if I'm differentiating with respect to y and the y is inside the bracket, then differentiation of y with respect to y will definitely be 1. But as I have told you that we will not be differentiating the equation with respect to y. So this case will not be seen, but just for knowledge purposes, let's suppose if I'm differentiating y with respect to y, then we'll get 1 out of it. When we differentiate x with respect to x, we get 1, right? So if we differentiate y with respect to y, we'll get 1 as well. And if we differentiate y with respect to x, it cannot be differentiated, and we get dy by dx. So let's suppose if we are differentiating with respect to y, and we are trying to differentiate x with respect to y. So now in this x, there's no y involvement of y. So how can this x be differentiated with respect to y? So if it cannot be differentiated, it will get attached to d upon dy and we'll get dx upon dy. Again, this has nothing to do with what we are going to cover, but this is just for concept clarification so that you are clear about what I'm trying to communicate. कि अगर मैं with respect to x differentiate करता हूँ y को, तो वो differentiate नहीं हो पाएगा और attach हो जाएगा. Similarly, अगर मैं with respect to y x को differentiate करता हूँ, तो वो भी differentiate नहीं हो पाएगा और attach हो जाएगा. राइट? यहाँ तक मुझे बताएं कोई सवाल है कि आगे मजीद एग्जांपल्स की तरफ जाने से पहले आई नीड एन एक्नॉलेजमेंट, राइट? आर यू पीपल क्लियर टिल हियर? इज एवरीथिंग क्लियर व्हाट आई एम ट्राइंग टू कम्युनिकेट? आर यू पीपल ट्राइंग टू गेट इट और नॉट? समझ आ रहा है नहीं आ रहा? थोड़ी एक्नॉलेजमेंट दे दें भाई, क्लियर लिख दें, सो दैट एटलीस्ट आई एम कंफर्टेबल दैट यस आई एम ट्राइंग टू कम्युनिकेट समथिंग एंड योर पीपल आर गेटिंग इट. Whatever I've tried to, अलिया मैंने अब तक जो समझाया है वो समझ आया है. अब नॉर्मल डिफरेंशिएशन से ये ऐसे डिफरेंट है कि अभी तो कुछ डिफरेंट हुआ ही नहीं है ना. बट वाई क्यूब की डिफरेंशिएशन कभी की है हमने, और अभी वो चीज एग्जांपल शुरू नहीं हुए हैं. एक्चुअली वी हैव नॉट स्टार्टेड those examples which are actually a part of implicit equations, right? So you are going to look at it now. I've just taken parts of it to clarify the concept that when we are differentiating y with respect to x, it cannot be differentiated and we are going to get dy by dx. Now, inshallah, you'll see now what I'm trying to communicate. Let's start. Let's move forward. Let's suppose if I'm trying to differentiate xy square. Differentiate xy square with respect to x. Then what will happen? If I'm going to differentiate xy square with respect to x, what will happen? We know that x and y square are product of each other, right? So when two functions are product of each other, we apply the product rule. And when we apply the product rule says one of the functions is u and the other function is v. And the product rule is vu prime plus uv prime, right? We have covered this product rule in the general category of differentiation. So let's suppose if we are going to differentiate it, then what order are we going to follow? First, we'll write v. So I've written v, y square. Then u prime. Differentiation of x will be 1, right? Why? Because x will be differentiated with respect to x. So the differentiation of x will be 1. So vu prime plus uv prime. Then u is x. I've copied that down. Then v prime, when it's time to differentiate y square, now there is a problem because we are differentiating with respect to x. And if we are differentiating with respect to x, y square, then there's a problem. So first we are going to differentiate the power, deal with the power, we'll multiply the power, we'll subtract the power by 1. And then at the end, when it's time for y, it will not be differentiated and we are going to get dy by dx. So when it was vu prime, it was fine because u prime was the differentiation of x. But when it was uv prime, when it was time to differentiate y square, then y square got converted to 2y. But when it was time for y, it couldn't be differentiated and we got dy by dx. So that is the application of product rule. Then this is a particular example that we will look at, that we have to look actually, because of which I was trying to build up the foundations up till now. जो आलिया आपको क्लियर नहीं था ना कि क्या सवाल A2 में एक्चुअली कैसे ये AS से डिफरेंट है, पुराने से कैसे डिफरेंट है, अब आपको पता चल जाएगा. So if we see an equation xy plus y square equals to 2x, we cannot differentiate and obtain dy by dx directly. How can we differentiate it? Y is not the subject. So if y is not the subject, we cannot directly obtain dy by dx. Then in such cases, what we need to do is, we need to identify that this is an implicit equation because y is not explicitly shown, because y is not the subject of the equation. That is why we have to differentiate the entire equation with respect to x. Differentiate the entire equation with respect to x. Right? So differentiate the entire equation with respect to x. So the first thing that we are going to write is differentiate with respect to x. WRT with respect to x. Differentiate with respect to x. Okay, so let's start. Let's differentiate xy with respect to x. So because this is a product, we are going to apply the product rule. vu prime plus uv prime. So vu prime, the v will come over here, which is y. U prime, the differentiation of x is 1. Then plus uv prime, so u is x. Then v prime, the differentiation of y is dy by dx. Because y cannot be differentiated with respect to x, so the differentiation of y is dy by dx. Then plus, after plus, we have to differentiate y square. Then y square, there's a power, we deal with the power first. Power gets multiplied, power gets subtracted by 1. Then when it's time to differentiate the function within the bracket, that is when it's time to differentiate y, it cannot be differentiated and we get dy by dx out of it. Then on the right hand side, after equals to, there is 2x. It can be differentiated with respect to x and we have got 2. So we have differentiated xy, we have differentiated y square, we have differentiated 2x. Now we can see that dy by dx is coming up at 2 places. So what is the bottom line? Whichever terms contain dy by dx, we have to take them on one side and we have to take dy by dx as common. For the rest of the things which do not involve dy by dx, we are going to take them to other side. So 2 was already there. If we take y to that side, then if we see that this is y plus x times dy by dx plus 2y dy by dx equals 2. Then we'll take y to that side. From here, we are going to take dy by dx as common. So if we take dy by dx as common, then it's x plus 2y. On the other side, y is shifted, so it's 2 minus y. Then if we are going to make dy by dx the subject, we are going to get 2 minus y upon x plus 2y. So ultimately, the dy by dx that we have got is 2 minus y upon x plus 2y. Now, because we are dealing with an implicit equation and we are differentiating that, the dy by dx is not purely in terms of x. Usually, when we used to see the equations in AS level, the equation, the y was in terms of x and the dy by dx was also in terms of x. But over here, the gradient function is in terms of y and x both. So this means if we have to find the gradient of tangent to a curve, we will not be only substituting the value of x, rather we will be substituting the value of x and value of y both. So dy by dx is 2 minus y upon x plus 2y. So this is one of the equations that we will be covering of this type. Equations of this type will be covered in A2 level, inshallah, in P3. So I think I'm trying to communicate what I've been able to communicate what is exactly required here. Alia, did you get it now? Everyone to acknowledge on chat as to whether they have understood example number 6 or not. जब भी y की बात आएगी ना, तो वो विथ रिस्पेक्ट टू x डिफरेंशिएट नहीं हो पाएगा. पावर होगी उसके ऊपर, वो डिफरेंशिएट हो जाएगी. लेकिन जब फंक्शन y की बात आएगी, वो डिफरेंशिएट नहीं हो पाएगा और dy by dx मिल जाएगा. तो ऐसा हर टर्म जिसमें y की इन्वॉल्वमेंट होगी, वहां से dy by dx मिलेगा. और ऐसे जितने भी टर्म्स होंगे, उसमें dy by dx कॉमन लेके उनको एक तरफ करेंगे, बाकी सबको दूसरी तरफ करके dy by dx सब्जेक्ट बना के निकाल देंगे. दिस इज द प्रोसेस. Yes, David, I have not got an acknowledgement from you. Are you clear with it or not? कोई सवाल है तो पूछ लें, वरना अंडरस्टूड लिखकर आगे बढ़ा दें. हाँ, एक्नॉलेजमेंट नहीं आई थी, एक्नॉलेजमेंट दिया करें. चलिए, छठा एग्जांपल हो गया. आप देखें, अब 2-3 एग्जांपल्स मैंने और बनाए हैं यहाँ पर. 7th एग्जांपल, डिफरेंशिएट विद रिस्पेक्ट टू ए cos square y. अब you know what the order of trigonometric function is. In general category we learned power, function, angle. So let's follow that. Although there is y involved, ultimately we are going to get dy by dx out of it. This is what is inbuilt, right? We know that because there is involvement of y, we will definitely get dy by dx out of it. But what is the process? Do we directly get dy by dx? No. We have to follow the entire process. So if it is a trigonometric function, then the order is power, function, and angle. So if we deal with the power first, then dealing with the power means multiply the power and subtract the power by 1. So I've multiplied 2 and I've subtracted 1. I've get 2 cos y. First step done, power. Then it's time for the function. The function is cos y. So the differentiation of cos y is negative sine y. So I've written negative sine y. Power delt, function delt. Now it is time for the angle. And angle is y. Now when we are differentiating the angle, that is y with respect to x, it cannot be differentiated. And that is why we are going to get dy by dx out of it. So dy by dx will come in the last stage when we are when we are trying to differentiate the angle. It cannot be differentiated because it is y. And that is why we got dy by dx out of it. तो पूरा रूल लगेगा पावर, फंक्शन, एंगल. पहले पावर को डील करेंगे, प्रॉपर डील होगी. फंक्शन को डिफरेंशिएट करेंगे, प्रॉपर डिफरेंशिएट होगा. जब एंगल की बात आएगी, क्योंकि एंगल में y है, वो डिफरेंशिएट नहीं हो पाएगा, वहां से dy by dx मिल जाएगा. So cos square y is 2 cos y into minus sin y into dy by dx. And simplified to minus 2 sin y cos y dy by dx. This is the 7th example. Then we're moving on to the 8th example. Differentiate with respect to x e power minus 2y. Now again, what is the rule for differentiating an exponential equation? The differentiation of exponential equation is we copy the exponential as it is. The exponential function is copied as it is. But after copying, we differentiate the power with respect to x. So if you are differentiating e power minus 2y with respect to x, the first step is copy as it is. we get e power minus 2y. Then we have to differentiate the power with respect to x. So when we are differentiating with respect to x minus 2y, then what will happen? Minus 2 is a constant. It will remain minus 2. But this y will not be differentiated. So we are going to get dy by dx out of it. So that is why over here I have written minus 2 remains minus 2. But out of y, it cannot be differentiated. So we are getting dy by dx from it. So e power minus 2y is e power minus 2y into minus 2 times dy by dx. Then I've made another example, ln 2y. This is ln 2y. Then ln 2y means difference ln of a function. The differentiation of ln function is the function comes in the denominator and the differentiation of the function comes in the numerator. If you remember the rule, I told you the rule. ln fx when differentiated gives you f prime x upon fx. F prime x upon fx. So this is 2y, 2y will come in the denominator, and the differentiation of 2y is 2 times dy by dx. The differentiation of y is dy by dx with respect to x. The differentiation of 2y is 2 times dy by dx. So ln 2y is 1 upon 2y into 2 times dy by dx. Then 2 and 2 got cancelled, and we have got 1 upon y times dy by dx. 1 upon 2y into 2 times dy by dx, simplified 2, 2 and 2 got cancelled. We have got 1 upon y times dy by dx. So with this, we have at least covered, and the details I've covered over here as well, that xy squared, the u is x, the v is y squared. Differentiation of x with respect to x is 1, so u prime is 1. Differentiation of y squared with respect to x is 2y dy by dx. Then we multiplied vu prime plus uv prime, and we have got this. So the working of this is done over here, right? So I've covered these. The 7 examples were already written over here. I've covered the 8th and 9th as well to cover the exponential and logarithmic as well. So just let me know if you have been able to understand all the rules and have you made the notes or not. If you have not made the notes yet, then yes, it's time for you to copy the notes. So copy the notes and then let me know if you're clear and done with all the things. If there's something bothering you, just let me know and I'll be more than happy to help you out with it, inshallah. Okay. So it's your copy time. Once you're done, just write clear and done. So we'll move forward then. If you have any questions, you can ask. All right. So moving forward, Alhamdulillah, students have done till here. Then moving towards the example, right? Of a pass. This is another. This is the past paper question actually, right? So we look at this example, which is from past papers only. An old past paper question, which is not in our current topical past papers. It's older, right? So good for understanding purposes. The equation of a curve is x cube plus 2y cube equals 3xy. Now, as soon as we looked at the equation, we realized that this is an implicit equation because y is not the subject, right? So we cannot just obtain dy by dx directly. Rather, we will have to differentiate the entire equation with respect to x. The first part tells us, show that dy by dx is y minus x squared upon 2y squared minus x. So once we have realized that this is an implicit equation, we'll differentiate the entire equation with respect to x. And then we'll make dy by dx the subject and we'll be able to express it, inshallah. Then the second part tells us find the coordinates of the stationary points of the curve. So we know that when we are going to differentiate, when we need turning points or stationary points, we equate dy by dx to 0. So first let's check out part number 1 and then we'll see what to do in part number 2. So the first thing is, as soon as we realize that this is an implicit equation, we are going to write differentiate with respect to x. So this is what I've done. First step, differentiate with respect to x. Then we follow the entire process. Look, this differentiate with respect to x, this x cube can be differentiated. So we got 3x squared. Then 2y cube cannot be differentiated. Yes, but it can be dealt partially because there's a power. So first deal the power. 2y cube becomes 6y squared. And then when it is time to differentiate y, we got dy by dx. So 3x squared plus 6y squared into dy by dx. Then it's time for 3xy. Now there are two functions being involved. So one of them is u and the other one is y. So what I've done over here is I've taken this 3x as u and this y is v. So v u prime plus u v prime. So v u prime. So y remains same and differentiation of 3x is 3. Then u v prime. So u and v prime. The differentiation of y is dy by dx. Then we saw dy by dx over here as well as over here. So we are going to bring both the dy by dx to one side. But before that, if we check out what we actually need to show, we can see that it's y minus x squared. So this means we need to, and even at the bottom, it's 2y squared minus x. So this means this needs to be shifted to left side rather than shifting 6y squared dy by dx to right side. We have to decide this as well, right? Even if we have mistakenly shifted to other side, we can always adjust at the end. But just to avoid any additional steps, we can always look at what needs to be shown. Always have an eye on what needs to be shown. This is extremely important. Whenever we are told to show something, we need to have an eye on that. So then what we have done, we have taken dy by dx as common. Yes, we have taken dy by dx. We shift this to left side. Then if we take dy by dx as common, it's 6y squared minus 3x. First, I've written the process 6y squared dy by dx minus 3x dy by dx. And 3x squared shifted to that side. So 3y minus 3x squared. Then if we take dy by dx as common from here, we get 6y squared minus 3x. And on the other side, we have got 3y minus 3x squared. Then if we take 3 as common from here, if we divide, cross multiply, then it's 3 common y minus x squared divided by 3 common 2y squared minus x. 3 and 3 got cancelled. And we have successfully reduced it to y minus x squared upon 2y squared minus x. And this was what we need to show. So we have successfully shown part number 1. The entire process was already explained before as well. It's just a passable question that I've shown for your additional concept clarification. Now the part number 2 says find the coordinates of the stationary points of the curve. So we know that whenever we need to find the stationary point or turning point, we equate dy by dx to 0. But usually when we equate dy by dx to 0, we directly get the x coordinates and we substitute the x coordinates in the equation of the curve to get the y coordinates. But over here, this is not the case. In implicit equations, because the gradient function is in terms of x and y both. So if we are going to differentiate, if we are going to get dy by dx in terms of x and y and we equate it to 0, we are not going to get the coordinates directly. Rather, we are going to get a function. And that function will be solved simultaneously with the original equation of the curve. And then we will get x and y both. Then we'll get x or y, either of them, and then we'll substitute in one of the equations to get the other one. So the process is a bit lengthier, right? Previously, we used to get x directly because the gradient function was purely in terms of x. But now when the gradient function is in terms of x and y both, so we are going to equate dy by dx to 0 and we'll get a function, an equation. And we'll solve that simultaneously with the original equation to get the coordinates. So this is what I've done. Y minus x square upon 2y square minus x equals 0. Of course, the denominator being cross multiplied becomes 0 and we'll get y equals x square. We'll get y equals x square from here. Y minus x square equals 0. And ultimately, we are going to get y equals to x square. Then after that, we have not been able to get the coordinates. So this is an equation. We are going to solve this equation simultaneously with the original equation that we have been given. So y equals to x square. We can substitute x square over here. So x cube plus 2 times x square whole cube equals to 3xy. If you're going to look at it, and substitute y equals to x square in the equation of the curve, x cube plus 2y cube. So x cube plus 2y cube. In place of y, I have substituted x square. X cube plus 2y cube equals to 3xy. Equals to 3xy. So 3x and y is x square. So x cube plus 2 times x square whole cube plus 3x into x square. We have substituted y equals to x square in the original equation of the curve. We have got x cube plus 2x power 6 equals 3x cube. Then what we'll do? Then if we take x cube to that side, it is 2x power 6 equals 2x cube. Then do not cancel the variable. Few students cancel the variable. I've always told you, whenever the variable is in the numerator, whenever the variable is in the numerator, we do not cancel the variables. Whenever the variable is in the numerator, we do not cancel the variables. Else we lose a root and we'll lose the marks. So we cannot afford to lose the marks. So what we have done, I've brought 3x cube to left side, 2x power 6 minus 2x cube equals 0. Then if I take 2x cube as common, I'll get x cube minus 1, x cube minus 1. So 2x cube times x cube minus 1 equals 0. Then I've got two possibilities, either 2x cube equals 0 or x cube minus 1 equals 0. From here, I'll get x equals 0 and I'll substitute it in any of the equations. The best one is the simple one is this, y equals to x square. So if x is 0, y is 0. And if x cube minus 1 equals 0, we get x equals to 1. And if we substitute x equals to 1, we are going to get y equals to 1. So we have got two coordinates, 0, 0 and 1, 1. So there's not just one stationary point, coordinates of the stationary points of the curve. Even the question tells us that there's not one single point, there are stationary points. So we have got two stationary points from here, 0, 0 and 1, 1. So this is the solution of the entire example, which has been taken from the past paper. This is a past paper question in the range of 2002 to 2008, somewhere. So definitely worth seeing and worth copying, inshallah. So that after this, inshallah, you'll be able to solve the past papers as well. So just copy this down and let me know if you are clear with it. Once you have copied, write done and clear so I can move forward. All right, moving forward. Last aspect, differentiation of inverse tangent function. Why am I covering differentiation of inverse tangent function over here? The reason is that it is somehow linked to, it is definitely linked to implicit equations. Although if we memorize the formula, we do not have to look at the entire process, and even the process is not very essential for us. So what we can do is, firstly, I'll tell you the formula directly, and then inshallah we'll look at how it is linked with implicit differentiation. So if we look at it, differentiation of inverse tangent function. So if y is equals to tan inverse fx, if y is equals to tan inverse fx, so we know that if the function is ln fx, the differentiation is f prime x upon fx, right? Similarly, if we have to differentiate tan inverse fx, the formula is inverse tangent function, right? Inverse tangent function. So tan inverse being applied on a function. So what is the differentiation of that? The differentiation is 1 upon 1 plus fx whole square multiplied by f prime x. This is the ultimate rule. This is the ultimate rule. This is the ultimate rule. What? The differentiation of the function will come in the numerator. The function will come in the denominator and will be squared, and 1 will be added to it. Just in case of ln, we used to see the differentiation of the function used to come in the numerator and the function used to come in the denominator. Similarly, over here, the function will come in the denominator but will be squared. The square of the function will come in the denominator. Then we will add 1 to it in the denominator, and the differentiation of the function will come in the numerator. So differentiation of tan inverse fx is f prime x upon 1 plus fx square. Now, if we are able to memorize this formula, then we are all good with it. In formula sheet, it's written like this. The differentiation of tan inverse x is 1 upon 1 plus x square. So look, this is x. The square of it is taken in the denominator, 1 is being added, and the differentiation of x is 1, so it is coming in the numerator. So not that particular formula is given that I've taught you just now, but this is at least written that tan inverse x is differentiated to give us 1 upon 1 plus x square. So this that we have covered is the entire rule, the entire formula. Tan inverse fx is f prime x upon 1 plus fx whole square. Now, one thing that I need to clarify this note, which is very important. Tan x whole square is tan square x. We all know this, right? If tan x is whole squared, then 2 will come at the top of tan, and we can write it as tan square x. But if tan x to the power of -1, tan x whole power -1 is not the same as tan inverse x. You know why? Because tan square x is not a separate function on the calculator. But tan x whole power -1 means 1 upon tan x. And tan inverse x is an inverse tangent function, which is different from tan x whole power -1. So as both of them are different, we should consider both of them as different, and we cannot treat them as same. So tan x whole square can be converted to tan square x, but tan x whole power -1 cannot be converted to tan inverse x. So these are both different. So even if we look at the example, tan x power -1 means 1 upon tan x. So if we find 1 upon tan 30, we'll get root 3. Tan 30 whole power -1 means 1 upon tan 30, we'll get root 3. But if we are going to calculate tan inverse 30, if you're going to get tan inverse x, that is, if you're going to calculate tan inverse 30, then the answer is not root 3, but it is 88.09 something. 30 is in degrees, so we have to work in degree mode. So 1 upon tan 30 means tan 30 whole power -1. Tan 30 whole power -1 gives us a different value, and tan inverse 30 gives us a different value, hence proved that tan x whole power -1 is not tan x whole power -1 is not the same as tan inverse x. Tan x whole power -1 is not the same as tan inverse x. So this is actually proved. The tan x whole power -1 is not the same as tan inverse x. And even if we differentiate tan inverse fx, then we get this differentiation. But if we differentiate tan x whole power -1, that is 1 upon tan x is cot x, right? We have already seen the differentiation of cot x in the general category. If it's cot fx, then it's 1 upon tan fx, and this is tan fx whole power minus 1. So differentiation of cot fx we already learned. Even if I'm going to differentiate it over here, then tan x whole power minus 1 is minus tan x whole power minus 2, the composite function. Power gets multiplied, the power gets subtracted by 1. Then the function inside the bracket, the differentiation of that is also multiplied. So tan x whole power minus 1 is minus tan x whole power minus 2 into sec square x. And then when it's term of angle, the angle is x. So the differentiation is 1. कौन सा rule लग रहा है? Power function angle. Power function angle. We multiply the power, we subtract the power by 1. Then it's time of function, then tan x is sec square x, then it's time of angle, then the differentiation of x is 1. So the bottom line is tan x whole power minus 1 is not the same as tan inverse x. Both are different, even the differentiations of both are different. Yes. Then if we look at the differentiation of tan inverse fx, which we are currently looking, then it's f prime x upon 1 plus fx square. If we look at the examples, then we have already seen in the formula sheet that the answer of tan inverse x is 1 upon 1 plus x square. How? If we apply the rule, then we know that the function x comes in the denominator and it's squared and 1 is being added to it. And the differentiation of this function is 1. It comes in the numerator. So we have got 1 upon 1 plus x squared. Then if we look at y equals to tan inverse 2x squared plus 3x, then the function will come in the denominator. It will be squared. 1 will be added to it. And the differentiation of this will come in the numerator. So 2x squared plus 3x once differentiated will give us 4x plus 3. So it's 4x plus 3 upon 1 plus 2x squared plus 3x whole square. So we do not have to simplify any further. If we are told to give it in a particular form, then we'll simplify it further, or else we can give the answer in this form as well. Right? Then if you look at the third example, then the function is x cubed minus 5. It will come in the denominator after being squared. So x cubed minus 5 whole square comes in the denominator. 1 is being added in the denominator to it. And the differentiation of this function is 3x squared, which comes in the numerator. So using these three examples, I have applied the rule and this formula has been applied. How to apply this formula? I've taught you using these three examples. Let me know if you are clear with how we applied this formula and how tan inverse x is different from tan x whole power minus 1. Are you clear with this? Are you clear till here? यहाँ तक बात समझ आ रही है कैसे tan inverse fs की differentiation की है और कैसे tan inverse x का आंसर tan x whole power minus 1 से different है. tan x whole square tan square x कहा जाएगा, but tan x whole power minus 1 को tan inverse x नहीं कहेंगे. Copy it as well. Copy it down as well. Copy these three examples. Copy this. This is yet to be done. So you can copy till here. Once you're done, just write done so I can move forward. Okay, so we are done till here, alhamdulillah. Then we I just have to teach the connection between implicit equations and inverse tangent function. That how this formula that we have memorized now has been derived using the concept of implicit differentiation. Although that derivation will not be asked, no one is going to ask you that derivation, but we just need to clarify that concept that even if, let's suppose, at times if we forget this formula, at least the connection between this inverse tangent function and implicit equations will help us derive this while sitting in the exam as well. So even if we forget the formula, we can remember the concept and we can apply or we can differentiate the function right there and then during the exam, inshallah. So this is important. And what is the connection? So here it is. Let's suppose if you are told to differentiate y equals to tan inverse fx and we don't know any formula, then what we can do? What steps can we follow? Firstly, we can shift tan inverse to left side. So when tan inverse shifts to left side, it will become tan y. So y equals to tan inverse fx. If tan inverse gets shifted to left side, it will become tan y. So tan y is equals to fx. This is the first step. Y equals tan inverse fx. Tan inverse shifts to left side, it will become tan y fx. Tan y equals fx. Then we see that this is just like an implicit equation. Because when y was the subject, we don't know how to differentiate. Let's suppose if we don't have the formula. But when we shift tan inverse to that side, now it's tan y and y is not the subject. So now what we can do is we can differentiate the entire equation with respect to x. So if we differentiate tan y with respect to x, then we know that differentiation of tan is sec square. So tan y is sec square y, but the differentiation rule is power function angle. So there is no power over here. So if you deal with a function, then differentiation of tan y is sec square y, and the differentiation of angle is dy by dx. Because y cannot be differentiated with respect to x, so we get dy by dx out of it. The main concept of implicit with which I started the concept today, with which I started the explanation today. So the differentiation of tan y is sec square y into dy by dx, and the differentiation of function of x will definitely be f prime x. Whatever the function is, that will be differentiated. As of now, we are talking in general terms. So that is why I've just written f prime x. Although if there was a function in terms of x, that would have been differentiated. We'll see an example as well. So then tan y gets converted to sec square y dy by dx. The differentiation of fx is f prime x. The differentiation of fx is f prime x. Then what happens? Then we shift sec square y to that side. So it's f prime x upon sec square y. But then we know that there's a trigonometric identity which tells us 1 plus tan square x is sec square x. So if it's 1 plus tan square y, it is identical to sec square y. So in place of sec square y, I've taken sec square y to that side. But in place of sec square y, I've written 1 plus tan square y using the trigonometric identity. So f prime x upon sec square y, then f prime x upon 1 plus tan square y, right? And then we know that tan square y means tan y whole square. We know that tan square y means tan y whole square. And we already know from this step that tan y is equals to fx. So in place of tan y, we substitute fx. So tan square y gets converted to tan y whole square. Tan y is equals to fx. So it will become fx whole square. So then in place of tan square y, I'll substitute fx whole square. So when tan y was tan inverse fx, the dy by dx was f prime x upon 1 plus fx square. So this is how this formula has been derived. Now, if you memorize this formula, which is very simple, the function after being squared comes in the denominator, 1 is being added, the differentiation comes in the numerator. It's perfectly fine. But if you forget the formula, then how has it been derived? Tan inverse shifted to left side, differentiate with respect to x. Tan y gets converted to sec square y dy by dx. Sec square y is 1 plus tan square y. Then tan y is equals to fx. So tan square y is fx whole squared. And ultimately, we have been able to derive the formula. If we apply this to an example directly, let's suppose this is the example. Y equals to tan inverse 2x squared. y equals to tan inverse of 2x square, right? Y equals to tan inverse of 2x square. And if we don't know the formula, we'll shift tan inverse to that side. So it's tan y equals 2x square. Then we differentiate with respect to x, then tan y gets converted to sec square y into dy by dx, and 2x square gets differentiated to 4x. Then if we make dy by dx the subject and shift sec square y to that side, it will become 1 plus tan square y. So it will become 4x upon 1 plus tan square y. Then we know that tan y is 2x square. So tan square y is 2x square whole square. So it's 4x upon 1 plus 2x square whole square. So this is how we have been able to obtain the gradient function in terms of x purely. Ultimate objective was to obtain dy by dx in terms of x only. And that we have achieved, alhamdulillah, using the entire derivation process. So although the derivation process is not required, we can directly differentiate it. We can directly differentiate as we have done in example 1, 2, and 3. But let's suppose if we forget, we should know the connection between the inverse tangent function and the implicit differentiation. So we will be able to do it, inshallah. So just acknowledge this was the last page of explanation. Just acknowledge if everyone has been able to understand, copy it down and let me know if you're clear and done with it. Alhamdulillah, everyone is clear and done till here, right? So, Alhamdulillah, the explanation of implicit differentiation has been completed. Now, I have covered a lot of past paper questions as well of implicit that I'm going to upload on the LMS as well, right? So, I'll upload the today's class, inshallah. I'll upload the past papers of implicit equations. And apart from that, the questions that I've already covered in the past, I'm going to upload the recordings of that as well. Then you can go on with completion of this topic, inshallah. Then solve the questions of parametric equations that I covered in the last class, implicit equations that I've covered in today's class, and then attempt the past paper questions, all the questions of parametric, implicit, and general category as well. And if there are any questions and problems, inshallah, we are going to look at it in the next class. We have no problems, we are going to move on to integration, inshallah. But if we have problems, so we are focusing on questions and problem solving first, inshallah. Okay. So I think today we are going to end till here. Alhamdulillah, our objective of today's class has been achieved. Take good care of yourself. अपना बहुत सारा ख्याल रखें. दुआ में मुझे याद रखें. Assalamu alaikum wa rahmatullahi wa barakatuh.